Alright guys, in this video I'm going to cover some more information about force diagrams and net external forces, including how to draw free body diagrams, because that's a pretty major topic that we're going to be focusing on moving forward. Alright, so first things first, I just want to go over some basics. When we see free body diagrams, there should always be a point representing the system being anything from a car to a child to a molecule. That single point simplifies things for us in a big way, and so we're going to stick with this particular type of system. Okay, next thing we're going to do is we're going to draw all applicable forces. Now, some diagrams will have what we call a normal, some will have a weight force, most will have a weight force, some will have an F applied of some kind. When we say F applied, we mean this could be a push, this could be a pull, this could be the force that something is experiencing by a system. Okay. Those F applied can point in any direction. They can be pushed up, they can be pushed left, they can be pushed right. And then another common force that we see is what we call friction. Friction, typically in our diagrams with a lowercase f, is always going to point opposite of the motion. And a lot of times what that really means is F applied. Okay? When we go to find F net, for now, what we are going to be focusing on is the x direction of our forces, because we're only dealing with XY diagrams. Reason being that in the y direction, the normal force is equal to the weight force. So we don't actually have a net force in the y direction, but we do have an F net in the x direction, and that is going to be the sum of all the forces that are added together to become the net force. Now, in this particular case, in this particular diagram, my F net is going to be equal to F applied plus a negative friction force, because friction is pointing the opposite way. Remember that things that go right are positive, things that go left are negative as far as vectors are concerned. So that means F applied minus friction will be our F net. And a lot of times we're going to need to know what F applied is or what friction are in order to get a net force, because then we can use that information to calculate mass and acceleration according to Newton's second law. Okay, so just kind of wanted to go over some basic stuff on free body diagrams. Another thing that I want to show you is how to interpret them. And these are free body diagrams. Still, they're typically represented with an FBD. Okay, all right, so I'm going to draw a couple of free body diagrams, and we're going to discuss what they're telling us as far as the direction of motion is concerned. Okay, let me do one more. I lied, two more. Okay, all right, so now here we have our first one. In our first diagram, this object is in what we call free fall. If it were in contact with a surface, it would have a normal. But since it's not in contact with a surface, there is no normal force. We know it's falling downward because there is no applied force here or here. So this thing that is currently falling must have no x direction. In fact, the only net force here is going to be that of negative W because it points downward. Okay, so this is an object in free fall. Free fall is awesome. And we'll talk about why here when we do a sample problem. All right, over here, the F applied is clearly drawn as larger than the friction force. Okay, so what that tells me is that F net is going to be a positive number that falls to the right, which means that it will have an acceleration that is also likely positive. Okay, down here we have F applied is still greater than F, but it is going to the left. So by definition, we would say that A is negative. F net would be a negative number. Okay, down here we have F applied equal to F, which that means that the net force is going to be 0. And you take F applied and you subtract the friction force, you get an F net of 0. What that means also then is that A will be 0. Okay, over here we have F applied is smaller than friction. When that happens, then F net is a negative number and A is likely also a negative number. Okay, all right, so in this particular case, acceleration is probably increasing, acceleration is probably decreasing over here, and you'll have to remember some of the sign conventions. If something is decreasing in the negative direction, it can be speeding up or it can be slowing down. What it depends on is the direction of the motion. So over here, in theory, the motion is actually to the right, and the acceleration is negative, which means this object is slowing down and moving right. Over here, the object is speeding up to the left. Up here, we have the object is speeding up to the right. So remember that F applied tells you the direction of motion as well as can help you identify the acceleration when it's plugged in for F net. Okay, so this is just a quick what is a free body diagram kind of thing. And we're going to practice more with free body diagrams here in the near future. Okay, so let's do some situational problems. This first one says an 80-kilogram skydiver jumps out of a plane. What is the net force of the skydiver as they fall? And so here we're going to draw our free body diagram. The only thing acting as someone falls or something falls is weight. We know that W equals M times G because that was something that was covered in this particular chapter. We know the mass of the skydiver is 80 kilograms. And we know the gravitational pull is 9.81 meters per second squared. Okay? The only other thing we want to make sure is, do we know what F net is? In this particular case, since it's free fall, F net is just going to equal W. And technically, it's going to be negative W. Okay? And forces can be negative, just in case you're wondering. So we're going to set up our equation. And we're going to get $784.8 newtons as the net force on the skydiver. All right, moving on. The next one has a car traveling on a road at 45 meters per second. It says that when the driver goes to stop, they apply a force of 2.5 newtons on the brakes. And when that force is applied, it's going to act opposite of the object's motion. And so what I'm going to do on here is I'm going to draw an arrow up here that just kind of tells us V is positive in the right to the right. So F net is 2.5 newtons. Since the motion is going backward, friction points forward then. Remember, it always opposes the direction of the applied force. The acceleration then is when we can, oops, this is not F net. This is the F of the brakes, right? Sorry. In order to find F net, we're going to do F of the brakes. Oops, sorry. In this particular diagram, the friction force is positive, so we're going to do friction minus F of brakes. Remember, everything to the right is positive, everything to the left is negative. So our F net would equal 1.2 minus 2.5, which is a negative 1.3 newtons. Makes sense because acceleration should come out to be negative. If we're trying to brake, acceleration should be opposite of the direction of our motion. And since our motion is to the right, acceleration being negative would mean the car is going to start slowing down. Okay. All right. So then this, we are going to set that negative 1.3 equal to mass times acceleration. We were told the mass of the car is 1800. So we're going to do negative 1.3 equals 1800 times A. Divide both sides by 1800. It's going to be a really small number. But our acceleration comes out to be 7.22 times 10 to the negative, 7.22 times 10 to the negative fourth. Whoa. Meters per second squared. Okay. All right. Next question. Deciding to speed up again, the driver accelerates at 2.3 meters per second squared. Okay. In this particular case, we don't really care about friction. We weren't told to care about friction. So I'm just going to set F net equal to M times A. The A is going to be the 2.3. The M is going to be the 1800. So F net, in order to get this car moving, is a very large number. Okay, so the acceleration value on the car is very small when it's trying to brake, but it's very large when we're trying to speed it up at this much faster speed. And that's just a brief introduction to identifying our forces. The other thing we could have probably done with part B is draw ourselves a diagram again. We've got the car. We're going to assume it's at rest because the driver was slowing down in the last problem. So it's not moving quite yet. The question is what force has to get applied, or what force is being applied in order to get this thing moving with an acceleration of 2.3 meters per second squared if it weighs 1800 kilograms. Okay, so just kind of keeping in mind that this is all the information we were given. Want to make sure that we're identifying our information as we're using it, and so on. Okay, that's all. I hope this helps a little.